Today is lecture number 13, and I plan also to give lecture next week, number 14, and that will be the last one. After that, if you recall, I will be happy to answer questions. Maybe I'll have some session with questions and answers, and there are already some problems on the website, and will be more. You're encouraged to solve them. Okay. This lecture and the next one will be a continuation of the topic which we discussed last time. It was about cluster structure on the spaces of local framed local systems. Last time we discussed the case of PGL2, and today we move further to higher rank PGLM. And this was probably the last formula which we had in the previous lecture. So today I will sometimes write G, but in practice it means PGLM. Whereas many statements and formulas can be generalized to any simple, maybe semi-simple Lie group, and better to say a joint type. The group without center. And the space on which we are going to consider is a space of framed local system, which means the follows. We have a G local system with additional choices. This is a choice of invariant flag on each marked point and invariant flag in each matched point and puncture. Maybe to better say a choice of flag for each marked point and invariant flag. What do I mean by this? So first of all, what is flag? Today we will have only complete flags. So I will omit this word complete. And the flag is just a sequence of vector spaces. F0 embedded to not equal to F1, embed not equal to F2, not equal to Fm, which is equal to Cm. And from this non-equalities follows that dimension of each Fk is equal to k. Our group PGLM acts on the set of all flags. Indeed, PGLM acts on the GLM acts on our vector space Cm. Hence, GLM acts on the set of flags, maps any flag to some other, and clearly this action on the set of flags doesn't depend on the action of the central GLM. So PGLM acts naturally on the set of flags. If we take a standard flag, then its stabilizer is what we have 0 embedded to vector subspace generated by first basic vector, generated by two basic vectors, and so on. Then its stabilizer is a subgroup of upper triangular matrices. So they should preserve first basic vector. So first column should be something 0, 0, 0. Then it should preserve the second basic vector may goes only to some linear combination with it and first vectors. So we have this form of the second column and so on. And this is subgroup of a triangular matrix, Borel subgroup. Hence, the space of flags can be identified with quotient PGLM by B. Here I will also use the fact that PGLM acts transitively on the space of flags, so we can map each flag to the standard one. This I hope is obvious. So, and maybe the last remark. For the case m equal 2, PGL2 case which we considered above, we clearly have space of flags is equal to P1. So in this case, we have only one flag, so the zero-dimensional subspace is 0, m-dimensional subspace is the whole C2. So the only freedom is the choice of one-dimensional subspace and two-dimensional vector space, and this is literally below. So in this sense, the space of local system, this additional data, which framing choice of the flags, is generalization of what we had above, the choice of the point on P1. Okay, this is what is flag, but you can ask flag where? Usually, here I define the flag just in the vector space CM. Do I assume that we have the same CM for each point? Actually not. Actually, this is a flag inside of the vector bundle which corresponds to this local system. So for any point, any marked point to puncture, P. So formally, it is said that P assigns the G invariant section of G mod B. But in other words, if we think about local system as a monodromy of the vector bundle, with flat connection, then to each point P, we assign a flag in the fiber of this bundle. And now we can make sense of this Word's invariant flag. Because if P is a puncture, we have here's our surface, and on it we have some puncture. I forgot, punctures. I forgot to let me look. I denote them just by dot of this color. We have a puncture, and then we have pass around this puncture, some pass gamma around P. Then we have monodromy M gamma, which locally can be viewed as a map from the fiber at P to itself. And the last condition that puncture flag should be invariant means that under this monodromy, this flag should go to itself. One can ask, what is the meaning of this auxiliary data? Is it how far our manifold is from the original manifold of the local system? And actually, it's not so far. Actual answer is actually not so far. Remark. If M gamma is generic, it means that M gamma is conjugated to the diagonal matrix with M different eigenvalues. Then, in order to have invariant flag, we need then there exist n factorial choices of invariant flag. Namely, for any permutation sigma in a cell, we can assign flag f sigma, which is 0, e sigma 1, so, for example, first subspace should be invariant under this monodromy. The only invariant one-dimensional subspaces are subspaces generated by one of the eigenvectors. So this is first choice. Then we should have two-dimensional invariant subspace. So we have to add another eigenvector in order to have invariant subspace, and so on. So here I actually use the fact that all eigenvalues are different. Otherwise, it's not. As we have actually continuous freedom in the choice of flag. Hence, if our surface S has no boundary, so the only problem is, so it has some marked point, some punctures, but no boundary, no marking points. We have a map from XGS to the just standard space of local system. And this map is here should be M, sorry, M factorial in power number of punctures to 1. Namely, for each puncture, we have to pick invariant flag, and there is M factorial choices to do this. And so this is a finite map. See, this is quite large, but finite and controllable cover. So locally, so this is a covering. So locally, this space is isomorphic. So in this sense, one can think about XGS as a close relative of the coordinates on the space of local systems. If the surface has boundary, then we have some continuous choices, because we don't have any conditions. Maybe this should be called the second another MO point. Boundary, we have no conditions. Indeed, if we take, say, triangle, we have here flag A, B, C, 3 flags. This B shouldn't be confused with barrel subgroup, which I also denote by same letter. Maybe I can't do anything with this. Anyway, so we have 3 flags, and we have no monodromy condition for different reasons. First of all, there is no, because we can compute, we don't have closed loop around A. We can compute the parallel transport from here to here, but there is no, it is not canonically defined. Because it depends on choice of the basis here and basis here. And we can change this basis such that A becomes invariant. There's no condition. Another point is, so we have no condition. This means that the dimension, hence dimension is greater than equals than the dimension of the usually greater space of local system. So usually greater because in each point we have additional freedom choices of flag. The only thing which is somehow reduces freedom because it's a gauge transformation which we have. For example, in case of reflex, we have this reflex, but we can act by G. So the dimension is 3 times G minus B minus G. Okay. So for triangle, dimension of EGS is 3 dmg minus B dimension of B and minus dimension of G, which is overall conjugation. So in total, it will be 2 dimensions of G minus 3 dimensions of B. I need a bit more space. And on the contrary, dimension of the space of local systems is equal to 0, since we have a triangle which is contractible. So the only local system is 3. Okay. Any questions so far? We're going to construct coordinates on the XGS, but it is convenient to consider also some relative of XGS, which is called PGS. And this definition is more recent. So XGS was introduced by Foka and Goncharov, and PGS were introduced by Goncharov and Shen. And the difference is on the boundary. So PGS is the same as XGS plus extra data, which is called Phoenix. So I have to define what is it, what are the Phoenix. Assume that we have 2 barrel subgroup, B in B prime in G. Assume that these 2 barrel subgroups are in general position. This means that the intersection which you can denote by H, is abelian. Standard example, of course, is B consists of upper triangular matrices and B prime. Let me, for speed, just copy this and then correct. So B prime is, instead of upper, we have lower triangle. Then the intersection is a set of diagonal matrices, and it is a abelian subgroup. As I said, this is a general position, consideration of general position. So if you conjugate these two subgroups somehow, then still there's a common conjugation of these two general position. The intersection will appear, and they can be conjugated to such choice B and B prime. Up and low triangle. Okay, so assume that B and B prime are like this. Now, pinning is the following data. For any simple positive root alpha E I check, we assign a homomorphism I from SL2 to G, such that upper triangular matrices goes to B, diagonal matrices goes to Cartan intersection, and lower diagonal matrices goes to opposite barrel. One can think about this as a choice of Chevalier basis. Basic example is the following. So if we work in a situation where B is upper triangular matrix and B prime is lower triangular matrices and H is Cartan, then this map phi I maps matrices of the form A, B, C, D, which belongs to SL2, to the matrix of the form 1, 1, 1. Then on I's place we have A, here we have D, and I also want to write here B, C. So this is a standard SL2 embedding, but actually we have a parameter. we can multiply here by lambda and here by lambda inverse, and this is still will be homomorphism. So choice of the ping is a choice of this lambda. If we have two barrel subgroup, then we have Cartan, we know our roots and so on, but we don't know precisely what is E, what is F. So in this terms, this is tertiary basis. We have H to H, but we can multiply E by lambda and F by lambda inverse. And for the same triangular decomposition, this will be another choice of the Chevalier basis. Another choice of the Chevalier basis. Not Chevalier, not basis generators. And so this is an additional choice. Triple. B prime and set of all phi I is called a pinning over pair of the barrel subgroup B and B prime. This definition, at least as stated here, was generic. It worked for any simple group, semi-simple group. Since honestly, I will work only with type A in PGLM. So in case of PGLM, this can be stated more explicitly. So PGLM. So this we have two barrel subgroup B and B prime. To each of them, we can assign a flag, which is invariant under the action of this subgroup flag. Let me denote them by F and F prime. So we have F0, which is F0 is equal to 0, which is embedded to F1, embedded to F2. Fm is equal to Cm. And similar to V prime. Okay. We had a condition, then B and B prime are in general position. This will mean that these two flags are in general position. B prime. What does it mean? It means that everything which can intersect. It means that dimension of the intersection is as expected. How to say? So if I take I-dimensional subspace in first flag and plus 1 minus I dimensional subspace in the second flag, then this intersection will be a one-dimensional subspace. In terms of, one can say also in this way. So if B prime upper triangular and lower triangular matrices, then flag which correspond to B is a flag generated first subspace generated by E1, then E1 and 2, E1 and 2 and 3, and so on. And flag corresponding to B prime will be flag corresponding to the same basis, but on the opposite direction. So one-dimensional space will be generated by EM, two-dimensional by EM minus 1, and so on. And this intersection will be subspaces generated by basic vectors. So we have this one-dimensional subspaces, and our full vector space CM is just the direct sum. And easy to see what I just stated, that Fi is L1 plus Li, and Fi prime is Lm plus Lm plus 1 minus I. From this and from this. This is just a statement of flags, and now we have a pinning. And let me put it as a problem. States pinning over this pair B and B prime, which is the same as line. Which is the same as okay, two ways to say choice of VI in each Li Z. And another way to say it is a choice of line P in CM, such that maybe here instead of this I can say the choice of VI up to common multiplication. And here we have the choice of line, and such that this is just choice of line, and the map we take line P, which is generated by some vector, which I don't know how to know. I don't know, generated by vector F, and Vi is a projection of F through which is here's L1, here's L2, here's P, here's a vector F, this V1, this V2. And another problem states that for any P prime, maybe I will not use this notation here for the line, just to know this line by generating element to keep P for the name of pinnings. So for any P prime pinnings, there exists a unique element G in group such that G and P equal to P prime. And this action is probably better to say adjoint action. B prime and image of here we actually use the fact that G is PGLM, G doesn't have center. Okay, so I defined what are the pinnings. Now I will use them, but is there any question? So this is auxiliary data, but the size of this data is not much. The size of this data for any simple root, we have one complex variable. So this is something like Cartan, additional Cartan, which we assign to two Borel subgroups. And now I can say what is PGS. Final definition. And assigned to any boundary segment. Okay, maybe some comments are in order. Remark A. If our surface S has no boundary components, then the spinning do not matter. Second, if it's actually have some boundary components, then maybe more generally, we have equality of dimensions. So dimension of PGS is equal to dimension of FGS plus rank of G, dimension of the Cartan subgroup, dimension of this H, times a number of pinnings. And number of pinnings is by definition number of boundary marked points. So maybe you can ask why here I said that ping is assigned to each segment, and here I assigned to marked points. But this is not important because the number of boundary segments, number of components are equal. Each boundary segment is bounded by two marked points, and each marked points correspond to two segments, so the numbers are equal. Okay. Maybe I wanted to give more remarks, but maybe before I should give an example. And again, it will be example of the triangle. So before we had so in case of XGS, we have this for XGS. This is a triangle, or another way to say it is a disk with three marked points on the boundary. This XGS, if you want to understand PGS, then we have to assign spinnings. To have some, yes, my notations will be P, Q, R. And you see, I assigned them to segments, but the number 3 is the same as number of vertices. Clearly, for triangle and any polygon, the number of edges is equal to number. What is the reason why people consider why Koncherov and Shen decided that original definition of the framed local system was not sufficient? The answer is I'll give two arguments. So advantages. Okay. We can define a basis more projective. basis on any boundary segment. So if we have some boundary which is bounded by two marked points, then here we have some B prime and P, and this unity defines some basis. Maybe this is clear from this property. So we have decomposition of the CM to some one-dimensional subspaces, and moreover, due to pink, we have basic vector on this in each of these subspace. The word projective stands for the fact that we have not just basis, but base model to the rescaling, to overall rescaling for basic vectors. This because we work with a gauge group PGL function. Hence, we can compute what is called Wilson loop. Or in other words, this is a monodromy, or better say parallel transport. From one boundary segment to another boundary segment. So if we have two segments on our surface somewhere, and we have some path, then we can take, so here we had B prime P, and here we have B tilde prime, P tilde. We have defined basis here. So V is projective basis here. V tilde is projective basis in another point. And using our local system, we can move this basis from P to P tilde. So we have parallel transport M gamma of P, and so M gamma is a parallel transport along gamma, and existent unique G such that G applied to M gamma of V is equal to V tilde. So we can move this basis through our flat connection, through using our local system, come to this point and compare bases which we have defined here and base which we defined here. And they either coincide or not. And the difference between them is it can be called a Wilson. So it does not look, it's actually a line. So one boundary segment to another. That's the version of the monodromy, but usually monodromy is defined for the closed loops. And here, due to this additional structure, we don't have to look for closed loops, we can just work with such loops. In particular, now we have a condition at each marked point on the boundary. So we have, if we have some boundary, we have boundary points on it, and we can compute a monodromy like this. And then maybe write G gamma. G gamma. At this point, I will denote it by say P. G gamma on flag which correspond to P. So we have invariant flag also in such point. Okay. This is one of the advantages. Now we can treat boundary mark points and punctures more in a more similar way. We have conditions of invariance of the flag everywhere. And another advantage, we can now glue okay, let me state it in gluing map is available. So what do I mean? That if our servers, I don't know whether it's connected or not. Assume that we have two surfaces. Here with marked points and probably with some punctures. But what's more important with marked points on the boundary. And we want to glue them. For example, via these two boundary components. So you want to go if you to what to you in this you will have surface now with 3 handles. Two boundary components here and here, and how many mark points you have here. You have these 2 mark points. Here's this, and also you'll have one more in the point where you glue these 2 boundary components. This will be maybe a little more clear if I write here. Like this. I can label mark points. This 1, 2, 3, 4, 5, 6, 7, 8, 9, and after gluing, here will be 1, 2, 3. This will be 4 equal to 6, 5 equal to 7, 8, 9. And I should draw these points. And in order to do this gluing, we have to identify local glue local system, and this is possible since we have a basis. So we glue bases on segments on corresponding segments. So we have segment 4, 5. It would be glued with the segment 6, 7, and segment 5, 4 will be glued with the segment 7, 6.
I'm sorry, we had 3 marked points on the one boundary and 2 on the other. How we can glue?
Here I glue them through this boundary, these circles. In each of them we have 2 marked points. How do we get 3?
If we have 3 marked points.
If we have different number of marked points,
yeah.
Then we can. You see, mark points, they not disappear. They become punctures. We cannot sell them. Actually, of course, this gluing require maybe it requires some conditions that is possible. Oh, maybe not. Maybe we can just. Yes, maybe we can just do. So here we have some bases v for 5. Here v6, 7, and existent unique g such that g v for 5 is equal to v6, 7, and similarly existent unique g's such that in particular, if we have triangulation of surface S, we can glue cluster glue, or another word will be amalgamate cluster structure on PGS from cluster structures on P triangle, PG triangle. This is what I'm going to explain now. So everything boils down to the triangles. Actually, similar it was for PGL2 case. We took ideal triangulation. In each triangle, we draw standard quiver, and then we glue everything. Now, what happens in higher rank? Okay, here are some pictures. How to do? Maybe so I prepared pictures, but maybe I'll show them slowly. So as again, return to the triangle. So what do we have? We have three. We have triangle. In each point, we have flag, and in each boundary segment, we have additional data pinning, which corresponds to the choice of the bases here and here. The connection in this case is trivial, because one can think that the flat connection is trivial. Local system is trivial because we have no fundamental group. The triangle is contractible. But still, if we have some bases here and bases here, we can have a monodromy in this direction. From, say, VBA to VBC. And this monodromy preserves flag B. Hence, it belongs to some Borel subgroup. So if we define some natural cluster structures here on the space of framed and decorated with pinnings, so local system of the triangle. In particular, we define some cluster structure on the Borel subgroup. But actually, we know some cluster structure in Borel subgroup, because Borel subgroup is a particular case of the double Breuer cell. And this is the first thing which maybe which I prepared. Now recall that if we take Borel subgroup double Borel cell, which is identity from one well group and W0 from another subgroup, then this is literally Borel subgroup. To think, should I look? We can look somewhere. What was my convention about this? But so if I have W0E, it will be B plus. So this is a remark from lecture 7. Anyway. I decided to put B plus here in order to distinguish with flag B, which I already put here. Maybe it will be better to be more economic with English letters and write here F1, F2, F3, and pinnings on the opposite, with the opposite ladder, P1, P2, P3. Then we'll have, I can ignore this plus, but still I keep it. The W0 is the longest element of the while group. For example, one can take this reduced decomposition. S3, S1, S3, S2, S1, S3, S2, S3. And similar pattern for this for PGL4, but the part for high rank pattern will be similar. Here is the corresponding network. Or if you prefer, bipartite graph. And here is the corresponding quiver, which has this form of triangle. So it is it is maybe natural to put this quiver inside this triangle here. So here we discuss in monodromy, which goes in this direction. And the corresponding quiver is like this. If we look to the monodromy which goes to the another direction, so maybe I can let me correct my conventions. So here F2, F1, F2, F3, and flag F2 is invariant. So here F1, F2, F3, we look to this monodromy, and so this is a quiver which I stole from the W0, which I already know. And here is another quiver, which correspond to the cyclically rotated monodromy. If I go in this direction. And similarly, one can expect the quiver like in this direction. So putting all this together, it's natural to assume. So we define as follows. Just glue all these things together. Here's a picture for PGL4, but you can clearly guess what happens if rank is higher. I usually prefer to draw quivers which correspond to some bipartite graphs drawn somewhere on the plane, on the circle, or on the surface. Here will be, in this case, one can also draw the corresponding bipartite graph, which is here. The vertices on the boundary, I wrote them in squares, which means that they're frozen. When we have quiver for W0 or for any algebras cell on the boundary, we have unbounded regions, and the corresponding vertices of the quiver are frozen. But if you glue, so each so maybe this can be stated as a remark. Quiver for triangle maybe this color has 3 rank G frozen variables. And if you glue, then this will be correspond to amalgamation of the corresponding quiver. X cluster varieties, if you want. So in particular, all so it includes including unfrozen vertices, which becomes internal. Let me give an example. So we can glue 2 triangles together and get square. Natural story. Then what are the quivers? So I continue to draw pictures for PGL4. So for each triangle in each boundary we have 3 vertices, and then the situation will triangle. Okay, so here what we have 3 vertices. We have 3 vertices here. And then everything else is triangular. So we have how to write it. Yes, maybe. Yes, maybe like this. So here we can also write this. Actually, I'm not sure about this arrow. Yes, maybe it's honest arrow, but we have also okay. So the honest version, honest way to write down everything is to go through bipartite graphs, which knows everything. And for quiver, we should somehow have in mind that some of the edges are half-ish, which they correspond to 1/2 in the matrix B. Okay, whatever. Okay, here is a one triangle, and orientation is like this. Okay, and here is a for another triangle. Let me draw a picture. Okay, here is the picture for another triangle, and the orientation for each small triangle, orientation goes clockwise. So should be here, here, like this. And then in this is a gluing, and we have frozen vertices here and here on the boundary of this square. So in total we have 4 segments on the boundary. So we have 4 times rank, in this case 12 frozen variable of vertices. But vertices here are no longer frozen, they become unfrozen. But this is a picture for one triangulation. And one can take another triangulation like this. And draw corresponding quiver. Let me put it as a problem. Quivers and bipartite graphs related for triangulations related by flip are mutation equivalent. And if you, so we can draw the quiver for this triangulation, and I'm saying that is in PGL2 case, it corresponds to one mutation, and in this case we have more. Okay, maybe it is check this for PGL3, PGL, just to be convinced. And as a corollary, we get a quiver up to mutation for any surface. And what I didn't explain, what remains, the question which remains is what is the relation between cluster variables? They should be coordinates on PGS. And theoretically speaking, what I explained before says that it's sufficient to see that for the triangle, then glue everything together. But anyways, this I didn't explain. And then another question is how to compute inverse map. Namely, how to compute monodromy from cluster coordinates. And this we will discuss next time. Okay. Are there any questions?